Hello and welcome to another Zodin session. How about that? So I have a breaking news for you guys. Python is slow. Yeah, basically we've been developing our own programming language for the past like 3 weeks, and we're developing this programming language in Python, as you can see. So yeah, it's kind of weird, I know, developing a programming language in Python, but that's what we're doing. And to be fair, the specific language we're using for doing that doesn't really matter because we're generating assembly code anyway. So the final result is actually quite fast, right? So it doesn't matter what's the host, like how fast the host language is. It only affects the process of compilation, how fast the compilation go, but the final result is just actually unaffected by the host language. But here's the interesting thing. On top of the compilation mode, our language also has a simulation mode. I think simulation is actually quite a bad name for this. I rather mean emulation. So what it does, instead of compiling the program, it emulates the program. Essentially, it interprets it. So we're interpreting a language using an interpreted language. And that is, unsurprisingly, very slow. But I didn't realize how slow that is until recently, until we tried to use this language for solving Project Euler problems. For those who doesn't know, Project Euler is basically a collection of computer science problems, right? You can find this thing in the description. I'm gonna put it in the description. Right, so there you go. I'm gonna put a lot of things in description, so you can find the source code of the language we're developing also here. And we already accumulated like a good playlist of the series of me developing this thing. So in here is the Project Euler. Honestly, I'm gonna also put the link to the stream where we were solving the Project Euler problems. So Project Euler solving stream, right? So all of that is gonna be in the description. All right, so, and we were solving the fourth problem, right? The specifics of this problem doesn't really matter. What matters is that we have two nested loops, right? So from 100 to 1000, right? So essentially, yeah, like a roughly 1000 of iterations, 900 iterations. And inside of that loop, we have additional loop, which basically factorizes the number, right? So we have essentially 3 nested loops. And let's take a look at how fast this program runs actually, right? So let's go ahead and compile that program. So this is going to be example and problem fourth. Actually, that example is actually Euler, problem fourth. All right, so this is how quickly it compiled and then run. Right, so as you can see, we generated assembly code, we compile the assembly code, and then we link it into the program, and then we run the program. We can run the program separately without the process of compilation, just to time it. Right, so the expected result is 906609. Right, and if we time this entire thing, it's relatively fast. Could have been faster, but it usually does not exceed 200 milliseconds, 200 milliseconds. So, and we can try to simulate that program, right? So a simulation will essentially not compile it, it will just try to interpret this program, and let's see how much time it will take to do. So I'm gonna put a sim in here, and I'm gonna put a time in here, and so it will go, if I remember correctly, like for 5 minutes. Roughly 150 milliseconds, 5 minutes. To be fair, 5 minutes is actually a pretty long time, so let's make a small cut and just like jump straight into this thing being finished. Holy moly, it actually took 8 minutes instead of expected 5. It took 5 minutes when I was not running OBS, but with OBS it actually added like 3 extra minutes. Okay, so as you can see, the program actually still works correctly. It produces the same result. It's just extremely slow. As a matter of fact, like it's like magnitude slower, and I never actually experienced the simulation mode being that slow. So the discrepancy was there, but it was not that many magnitudes. So there's something really fishy going on in here. And to be fair, like the performance of the simulation mode got so bad to the point that I don't consider it useful anymore, and I was like seriously thinking to completely remove it from the language. But here's the thing, I think the simulation mode by itself, like Python and like, performance aside, is a very useful thing because you're essentially executing a program in a sandbox environment and you have a full control of that environment, and you can, for instance, gather some interesting metrics about the program you're running without compiling it or without, using something platform dependent, right? So it's actually a pretty cool sandbox that can give you a lot of insights into the into your program that you're simulating. And so here's another thing that something is fishy is going on. I think Droka, one of my viewers, actually rewrote the simulation mode just for shits and giggles in Go, right? So I'm gonna put their implementation in the description. So here it is. Porth simulation in Go, right? So this is where we're gonna have here. And here's an interesting thing for, I think, for Rule 110 specifically, right? So we have a bunch of examples for written in our language. So for Rule 110, the simulation in Python was 4 seconds, but when we written in Go, it actually went down to 26 milliseconds, right? Dramatically faster. So basically the problem is probably with Python somewhere. So if we used like a different language, we wouldn't have to remove the simulation mode, and simulation mode would have been feasible, right? So what I decided to do, I decided to try to look into how we implement the simulation mode in Python and see if we can improve something, right? And see if there is any particular operation within the simulation mode that is extremely slow, maybe some sort of a bottleneck that we can fix and improve the performance of this thing overall. So, and let's take a look at it. Let's take a look at how the simulation is implemented generally. So it's implemented in a function called simulation, actually simulate little endian Linux, right? It accepts a program, a sequence of operations, or a sequence of instructions of a bytecode, and just iterates over them, and it has a huge switch case, and it just interprets them, right? So, and what I want you to do, I want you to add some sort of instrumentation for each individual operation and each individual intrinsic, and just gather how many times a particular operation was executed to just see what's the hottest operation for that specific program, and also maybe gather some timing, right? So for like how much time the program spent executing that instruction and that intrinsic. And maybe if we run it for the problem 04, we'll gather enough insights to actually see where's the problem, right? So maybe there is one particular operation here that is extremely slow, and if we fix and speed up that instruction, the simulation mode overall is going to become faster, right? So, but we don't know what that instruction yet. So to know that instruction, we need to do some measurements, right? So how we're going to be doing measurements? Let's actually create some sort of a table, all right? So OP stats, all right? So I want this thing to be some sort of a dictionary that maps OP type to, let's say, an integer, and this is going to be essentially a count, or how many times a particular operation has been executed. So as far as I know, dictionary is not particularly convenient because it doesn't really have a default value, does it? Maybe we can make it have a default value. Maybe we can pre-initialize it with default values or something. So if I have something like this, and if I query something that doesn't exist, it will essentially tell me, well, basically throw an exception. I cannot just do +1 and assume that it's going to be defaulted to 0. Maybe there is a way to do a default. I remember there was something like set default. but I don't quite remember how to use that. Can I just set default to 0, right, and then just do +1? Probably doesn't work like this. So luckily, operation type is enumeration. So one of the things we can do, we can probably make this entire thing a list. Right, we're going to be making it a list. And then we're gonna create a list of the size of the operation types, right? So operation types, as you can see, class OP type is enumeration, and if you take a length of this thing, it will give you this thing. It will give you eight enumeration values. So we can create a list, and now we should be able to access the OP stats by doing something like OP type, right? So by doing something like OP type, and then do +1 because all of them are initialized with 0. I think it's actually kind of useful. Okay, so I think it would make sense to actually bump the operation counter at the end of the iteration or after the types are checked correctly, and we're trying to get a statistic for non-existing operation. So this is where we're gonna be doing all of that, right? Oh shit. Okay, so yeah, we have a pretty cool flag in here, a debug flag. It's only enabled if you provide -debug before the subcommand of the compiler. So I think we're going to be printing this stuff in the debug mode, right? So I'm not going to print the memory dump, and in here I want to do something like OP type in OP type, and here I'm going to just print the statistics. So this is going to be the name of the operation, and this is how many times the operation has been, you know, encountered, has been executed rather, right? So this is going to be OP type, and then OP stats, OP type. There we go. So if I try to run it, let's actually run it on a smaller program, something like simulate, maybe tests, right? And it's going to be a stack, right? So stack porth. Okay, so we have some problem in here. List indices must be integer or slices. Okay, so since enumeration is not an integer, I cannot use it as an index, which is kind of sus, not gonna lie. But here's an interesting thing. Can I just convert enumeration to an integer? Let me load the porth compiler into the shell. There we go. So I have something like OP type, and let's take a look at push int, right? Can I do just int? Must be a string. I cannot even convert it. Okay, so there must be a way to do that. Python enum to int. Okay, so int. So there's something called int enum. Base class for creating enumeration contains that are also subclasses. Oh, this is perfect. This is exactly what I need. So I think what I just have to do is I have to do int enum, and also I probably need to import this entire thing. Right, so by default enum doesn't act like an integer, right? So if you want it to act like an integer, you have to, you know, inherit a different thing. Okay, so I didn't enable the debug mode. Let's quickly do that. And list index out of range. Why would it be out of range? This is kind of strange. Don't they start from 0? Don't they start from 0? Wait a second. So if I go and do, okay, so the first one is push int, and it's are you serious? It starts from 1. Oh, Jesus Christ. Okay. So OP type. So what I have to do in here, I suppose I will have to do -1 here and in here. All right. I wonder if I can specify the starting value somehow. Anyway, so here we can see that for such a simple program, the hottest instruction was intrinsic. But to be fair, intrinsic, like, it's not very useful operation, and also I did a fucky wacky, I suppose, and a little bit of a oopsie doopsie. I keep forgetting that you have to do formatting like this, right? There we go. So this is what I expected in here. Intrinsic is not very useful because there is a shit ton of intrinsics which act like their own separate operations. So in fact, we have 29 intrinsics. So which one of those intrinsics was exactly, like specifically slow, right? We don't really know. So which one of 29th? So I think we need to have like a separate table for intrinsics as well. So int interstats, right? So this is going to list int length for intrinsic. Intrinsic is also enumeration, and since it's enumeration, I suppose we'll have to do int enum for this thing as well. All right, so this is where we handle intrinsics, right? So this is how many of them we have. So it's actually quite a lot of intrinsics, not gonna lie. Some of them not even implemented properly, but primarily the syscalls, right? Because to implement the syscalls, you have to simulate Linux or any other operating system you're simulating. So interstats, the type of the intrinsics is located in the operation operand, right? And we have to do -1, and we have to bump this entire thing. So what I'm thinking is that after we printed this thing, we want to check if the OP type is OP type intrinsic, right? Intrinsic. And if it is intrinsic, let's actually do like a similar dump of the table, but with a little bit of indentation for the intrinsic cell. So we will see that operation intrinsic took was this amount of times, but specifically for each individual intrinsic, there will be a separate counter. So inter type in intrinsic, right? And here we're gonna have space s d op type, not a p type, but inter type, inter stats, inter type -1. Alright, so let's see if it will give us more information in here, and it does in fact give us more information. So now we can see that the hottest intrinsic is print, so we're primarily printing something. We're not doing much, we're not doing any arithmetic operations at all, we're primarily printing things. For different kind of programs, we're gonna have different things, I suppose. For arithmetics, it's gonna be primarily arithmetics, I would presume. Right, so how many arithmetic operations we have in here? Not that many, actually. So, well, in arithmetics test, we just test each individual arithmetic operation, so there's nothing special in here. We can take a look at more sophisticated programs like examples rule 110. Right, so this is the most sophisticated program. So you see how slow it is in the simulation mode? It's just unbearably slow. Holy shit, that's a lot of operations. So I suppose the hottest one is memory. Right, so not even memory plus, actually 77,000. Right, so the plus was the hottest one. But here's this interesting thing. So the amount of times a particular operation or intrinsic executed is not very useful, because it may be executed a lot of times, but it could be super fast. On the other hand, we can have a very slow operation that is executed few times, but the accumulated time it took was longer, right? So maybe we also have to measure how much time it took to compute all of these instructions, and that will give us more information about what's going on under the hood. So we need a way to time the execution of the programs, right? So we need a way to say, okay, so let's take the time step starting from here, and after we finish the executing operation, we want to take another timestamp, find the difference, find elapsed time, and add that to the statistics as well, and then output it in the final table. I think it's going to be rather useful. So Python time execution. Is there any convenient way to do that in Python? How do I get time of Python program execution? Okay, Stack Overflow. Please enlighten us. Okay, so we can just use time, and okay, so that gives, but what's the resolution, right? So is the resolution in seconds? I want to have a resolution in microseconds and preferably even nanoseconds, because some operations can be very, very fast, but accumulated result is going to be very slow because there's a lot of such operations, right? So I want to have a predefined resolution. Okay, so we're going to have a time, and all right, so it's a float, if I understand correctly. So is there doubles and floats in Python? I don't know, maybe there's only floats. Okay, and it goes down to microseconds and a little bit down to nanoseconds, but it could be like just like an error or something. So we can assume that we have a resolution of microseconds, which is not that bad. I think we can work with that. All right. So let's import this entire thing. So this is going to be time. Simulation of our nation. So where are we going to keep all of that stuff? Where are we going to keep all of that stuff? I think I would like to keep it in here like so, but I think the tuples are immutable. In here, I think the tuples are straight up immutable, so I think it's going to be kind of a pain in the ass to work with. So if I have something like this, I won't be able to do things like, yeah, the tuples are immutable, you cannot just do that. So maybe we could have a separate tables. So okay, let's actually rename OP stats, maybe even stats to count. Right, so this is the count now, and we're gonna have a separately OP time, which is gonna be a list of floats. All right, and here we're gonna have something like len OP type, and similarly we're gonna have intrinsic time, which is a list of floats, 0 len intrinsics. Right, so we're gonna collect information about all of that. Alright, so we're gonna start the measurement from here. So this is gonna be time, and when it's about to do inter count, right, so we're gonna do inter time operation like this, start minus time, there we go. And when it's time to measure the whole operation, we're gonna do something like OP time, OP type -1 plus start minus time. There we go. So now we can do something like this. So times, and maybe in the parentheses we're gonna do something like f6. That's right. Very funny word. So OP time OP type -1. So this is the timing for this thing, and the timing for the intrinsics. So inter time inter type. Can I actually just keep it somewhere up there, because yeah, import type. -1. Is it working? All right, so let's see what's gonna happen. So far so good, so it doesn't crash anything. So maybe we're gonna have some interesting timing information. So, and it's negative because I'm an idiot. You're supposed to subtract the end from the start, not the other way around. Oh my god. That's why I'm unemployed. That's literally why I'm unemployed. That's why I'm streaming on Twitch. I'm not even streaming on Twitch anymore. All right, so what do we have in here? So what's the hottest operation in your area? So the hottest one is intrinsic, and we spent 3.5 seconds just executing intrinsics and nothing else. And the whole execution was like 5 seconds. And within these 5 seconds, we primarily did plus. Plus took half of a second. And swap. Swap was actually kind of slow, also half of a second. So yeah, apparently swapping things is actually kind of slow. Interesting. So I think we have all of the necessary information, right? And I think we can try to run this profiler, whatever the fuck it is, on the problem 04, on the problem that takes 8 minutes to compute, when if you compile it to assembly, it takes 200 milliseconds, right? So, and maybe after that we'll get some insights on what the hell is going on in there, and what's the slowest operation, and can we improve anything at all. All right, so let's go ahead and do that. I'm gonna try to simulate the Euler problem 04, right? And let's just cut into the final result, because I'm pretty sure it's going to be even slower, because on top of just simulating and running OBS, we're also profiling, we're also collecting information. So it's probably going to be like 10 minutes, I don't know, we'll see. So, welp. It took 11 minutes. So let's take a look at the data. So yeah, we can already see that do. Holy shit, that's a lot of, like, it's a 6 million times for 15 seconds. Like, the modern computer can do so much, like, within 15 seconds, way more than 6 million operations. Like, come on. So okay, so we can already see pretty hot things in here, like 105 swap, drop, and over. Huh, this is very interesting. Okay, let me actually save this information, because this is a very important and very valuable information, and I don't want to wait another 11 minutes just to gather that. So we're going to do something like problem 04 prof, right? So this is where we're going to save all of that, and I want to actually align everything a little bit so I can read it. Okay, so none of that was actually executed. So 13, 15 milliseconds are not that interesting. So these are the most interesting operations, like swap, drop, and over. Like, yeah, I wouldn't expect this thing to be so slow. To be fair, what I expected to be slow in this particular situation is a memory access, things like load and store. Because we are, if you take a look at the problem itself, right, so problem 04, we are using load 64 and store 64. So we're loading and storing 64-bit numbers in and from the memory. And here's an interesting thing. Our language does not support that. It only supports loading and storing 1 bytes. And, well, we do plan to actually implement that properly, but what I did as a, like, half of a joke is I implemented load and store 64 byte by byte, right? So essentially, if you want to load 64, we'll just iterate 8 times, and we just, like, you know, build a 64-bit number out of bytes, and we do the same for the store, right? I just want you to see how slow is it going to be, and I expect it low-key that this was the bottleneck of the execution, and I was hoping that like, I'm gonna just, like, make these things intrinsic and I'm gonna gain a huge speed up. But in reality, the memory access is like less than a second. Like, yeah, so the program was actually waiting primarily on swapping, dropping, and doing over, basically the stack operations, something that should be insanely fast. So I'm actually, yeah, this is really weird. Like, and essentially what swap, drop, and over means is that swap swaps elements on the stack, drop removes the element from the stack, and over copies the element below the top. Right, it's just like a stack operations. And what do we do? What do we use for the stack is actually just a list. Like, I would expect lists, the most common data structure in Python, to be very fast, right? It should be the most optimized data structure, but why is it so slow? Right, so stack is the list, right? So it's kind of sus, not gonna lie. Let me actually do something. Let's create a file, something like stack stress. Let's actually stress test the stack. Right, so I'm going to do user bin environment Python 3, and let's just create a stack, nothing special. So like this. And how many times this instruction is executed? So swap is executed 15 million times. Okay, so let's do the following thing. For I in range 15 million, right, like so, 15 million. And what we're gonna do within this loop is just basically push 69 and pop. There we go. So, and also maybe we are going to time this entire thing. So let's do something like start, time, and in here we're gonna print f6, haha, time minus start. There we go. So, and let's just go ahead and execute this entire thing. So let's see how, like, a pure pushing and popping on and from the stack is going to perform. So 15 million times is actually shouldn't be that many, operations. So it should be relatively fast. In any sane language, this should be like below 1 second. It must be below 1 second. And let's see. So we can put, oh, it's append. I keep forgetting that it's append, in fact. Are you serious? Really? Wait a freaking second. Just such a simple thing that has to be optimized because it's so common. Is that slow? I can't even properly, print this entire thing. I'm so in shock that I forgot how to use Python. It shouldn't be that slow. Seriously? 15 million times pushing and popping on the stack is 6.5 seconds? Really? So just to show you why I'm in such a shock, let's take a look at C++. Okay, so I know that comparing C++ and Python is kind of like an unfair game, but I'm going to disable all of the optimizations, right? So I'm going to tell the compiler it generate the most dumb assembly that you can generate, right? And let's write a similar program in C++, right? So we're going to use a vector, right? So, right, we're going to allocate the vector on the stack. So this is going to be our stack. So what I'm going to do in here, I'm going to just do 15 million times. Does 15 million even fit into the integer? I think it does. I think there should be fine. Right, so this is 15 million, right? So that, I think in C++, my C++ mode cannot support that, so I have to use a proper C++ mode, unfortunately. But it's extremely slow in my Emacs. Anyway, so, and in here I'm going to do stack, push back, right, so I'm going to do 69, and then stack, what the fuck was that? I think it was trying to outcomplete something, but then it just like turned into a horrible mess. Okay, so let's try to compile this entire thing, and I'm gonna tell the compiler, 0. You see, I'm disabling all of the possible optimizations, right? So it's not gonna like do any trickery. It will generate like very dumb assembly, right? And we're gonna do something like main cpp, right? And let's just like try to compile this entire thing and see how much time it will take to push and pop from the stack using C++. It was less than a second. Less than a second with all of the optimizations turned on. Really? It's like magnitude faster. Magnitude faster. And I'm really not sure what Python is doing. So if we take a look at with optimizations, right, if we crank up optimizations, I think it could be even faster. I think it would be even illuminated. I'm pretty sure the compiler just saw that I'm not even using the result for anything and it's just like straight up like stripped it off. But yeah, without the optimizations, it has no rights to actually strip it off. So it was like less than a second, right? It's just like almost a second, but it's not 6 seconds. Come on. You can do so much within 6 seconds. It's insane. So, I don't know, I don't like the conclusion to which we're coming so far, and the conclusion which we're coming so far is that it's the problem with the language, right? And it's just like, how can you optimize that? Right, so if we take a look, so this is the most basic operation, and there's nothing to optimize in here, you're just pushing and popping, so... I don't really like this conclusion. Though, there's one last thing we can try to do. We can't fix the language, but we can try to change the implementation, if you know what I'm talking about. So have you guys heard about PiPi? This is actually a very interesting thing. PiPi, well, it's kind of advertised to be a Python implemented in Python, but it's not necessarily true. PiPi is implemented not in Python, but in something called R-Python, which is a restricted subset of Python. It's so restricted that it's translatable to C, right? So, and that's why it's faster than the CPython implementation because essentially it's like implemented in C but in restricted Python that is translated to C. I like looked briefly into this entire thing, so I might be wrong, but it's claimed to be faster than Python, and also it has a JIT compilation. So and even Guido van Rossum said that if you want your code to run faster, you should probably just use PiPi, right? So he said it himself, creator of Python. Excuse me. And maybe that's what we should try to do. So maybe we should just see if using PiPi instead of C Python would make it faster. So let's actually go ahead and download. So maybe I'm going to take the third one. I can't right click because my Chromium is dumb. So I have to fix it yet again. Just a second, I'm sorry. All right, so I'm going to copy link address and I'm going to download this thing right inside of my port. And it's going to take some time, apparently. Maybe I have a slow internet. Maybe the internet on the server is rather slow. Well, the last time I used PiPi, it was rather fast. So I don't know if it's still as fast as it used to be. We're about to find out. Okay. So let's unpack this thing. So it's just like a regular package. It has a bin folder. I can already see that. And yes, cowboy freaking this. Okay, cool. Looks good to me. So if I try to run this entire thing, so this is going to be PiPi. I cannot see shit in this mist. Bin PiPi. All right, so it even has like the the shell of Python, so everything looks okay so far. Now, what if we run the stack stress using this thing? Well, it's actually faster than C++ without optimizations. I'm not even fucking joking. C++ without optimizations. It's faster than C++ without optimizations. The fuck? Wait, what? Really? So what if we try to use PiPi for the porth? Can we do that? So PiPi bin PiPi, and I'm gonna do porth, and let's actually try to run something that is not very heavy but reasonably heavy, rule 110, and let's see how much time it will take. So I didn't do that correctly. I should have put a simulation mode in here. It feels faster. It actually, so the startup is very slow. I presume this is because it maybe compiles something up front. It's kind of similar to JVM, to be fair, because JVM also has a very slow startup. But once it warms up, it can actually JIT compile like hotspots, and it runs very, very fast. So maybe the same thing goes for PiPi. So the startup time of CPython seems to be really fast, but it runs slow, right? It's already started, but it, you see it runs very slow. But for PiPi, it takes a little bit of time to start up, but then it actually goes very fast. And if we take a look at the timing, so yeah, it's 1 second, so it's actually more reasonable, yeah. So, and it doesn't complain, so it's completely compatible with our source code. It even supports the typing. I was actually afraid to use PiPi for ports because I was thinking maybe it doesn't support the typing and stuff like that, right? So, where's the typing? It's all because we're using like optional typing to check things around. So, okay, let's go ahead and try to use that thing for the Euler, right? Euler problem 04. Is it going to be even like reasonably, is it going to be like 1 minute, or how much time it will take? So it's already taken, okay, so I don't know, maybe we'll have to cut the entire thing, but maybe we can wait a little bit because it actually speeds up dramatically. Also, maybe we should probably disable the profiling and stuff like that. Okay, let's actually cut and wait until it actually finishes this entire thing. All right, that was actually faster than expected. 30 seconds, 36 seconds. It's actually, well, it's way better than 10 minutes. Yeah, it's 20 times better than 10 minutes? Yeah, it's not bad. So what if I disable the profiling and stuff like that? Let's actually straight up remove the profiling. Simulate, and it's also going to be probably faster without the OPS. So let me straight up remove the profiling, right? So, and to check things around, I'm going to use my Pi because it will tell me what other things I have to remove from here. So porth, well, that's rather slow, maybe. Okay, so we need to remove that. Another one, OP count, and also maybe I should have just commented it. Okay, so let's not remove this entire stuff because I think it might be actually useful in the future. So I have a tendency to implement useful stuff and then remove it and then regret it removing it. So let's actually get out of that habit. Right, so I don't think it's a very healthy habit. All right, so I disabled the profiling, and let's see if it's gonna speed up the entire thing. So let's just wait a little bit. So it should be like half of a minute, so maybe I'm not gonna even cut it. Because if it's less than a minute, the simulation actually becomes feasible, and maybe this is something, 20 seconds. This is something that we can already kind of run on CI, which is not that bad. So maybe I should completely switch to PiPi. Because why not? So yeah, so it's pretty good. So why do we need CPython? Why people still use CPython? PiPi is actually way better. Right, so, and sometimes it's even faster than C++. So, all right, I guess from now on, I'm gonna switch all of my development to PiPi. PiPi is actually a very interesting thing. It's highly compatible with CPython. So it's even runs like a popular libraries like Django. And stuff like that. So yeah, if you never heard about this thing, give it a try. Apparently it's actually a pretty cool thing. So maybe that's the future of Python. Maybe that's what everyone should use instead of CPython implementation. Yeah, I don't know, it's pretty cool. So I wonder, like, also it supports typing. Can it actually gather a useful information out of the typings and just like, yeah, maybe with the help of PiPi in the future, Python will become like a proper statically typed compiled language, finally. Yeah, I don't know. In any case, from now on, I'm going to actually migrate all of my development environment and infrastructure to PiPi, and we're probably going to run this entire thing on the CI in PiPi. Not like it matters, because we're going to rewrite the whole thing in Porth in the future anyway, but a little bit of a boost up in execution is going to help us to get that faster. And now I don't even have to remove the simulation mode anymore, right? Because with PiPi, it's kind of feasible. It still kind of sucks with 20 seconds, but it's not 10 minutes, and without OBS it's probably going to run even faster, and on the Microsoft CLI it's probably even faster than that, because their virtual servers are faster than my laptop. So yeah. So I hope today's session was interesting for you. It was definitely interesting for me, so I gained a couple of interesting insights. So thanks everyone for watching. Check stuff in the description. Right, I put some links in here. I think I'm gonna put the link to PiPi to the description as well. Right, there we go. And I think I'm going to go. Right, I think I'm going to go. Thanks everyone for watching. Love you all. Mwah.